this video, we will consider the range of conceptual or mental risk assessment models that are in use. These models, by the way, are not to be confused with the computational kinds of risk assessment models. You've already been exposed to a couple of them in the Glimmerous and Vibrio and Oysters risk assessments. This is an example of a conceptual risk assessment model. It's the one found in your text. We'll talk more about it later. For now, I'd like you to understand that these are the kinds of risk models we mean to explore in this video, the conceptual risk assessment models. In contrast, we have the actual computational models that are built as part of a risk assessment, like this computational risk assessment model for the Vibrio and Oysters risk assessment. Notice the elements of the conceptual model are reflected in the computational model. Here's one more computational model. This one is used to calculate expected annual flood damages. The details of the calculation are not important to us for now. Just notice how the elements of the conceptual model find their way into the computational model. This connection illustrates the value of having a conceptual risk assessment model. Your text offers one for those who do not have a more specific model for their own community of practice. There are many conceptual models in use. No one definition can meet the needs of the many uses of risk assessment, given the wide range of hazards found in the world. The communities of practice are so very different that it's unlikely that we will ever see one common definition or one single model of what risk assessment is or how it should be done. Your text definition says risk assessment is a systematic process for describing the nature, likelihood, and magnitude of risk associated with some substance, situation, action, or event that includes consideration of relevant uncertainties. A generic risk assessment model is also presented in your book and at the end of this video. It's one that serves a wide range of needs. In the United States, risk assessment is used by countless private sector organizations and businesses. It's also widely used in the public sector, as this slide suggests, by identifying some of the central government agencies that use risk assessment. In looking at these conceptual models, we begin by considering what risk assessment is. Most importantly, it's the science-based component of risk analysis. Risk assessment entails a set of logical, systematic, evidence-based analytical activities that are designed to gain an understanding of the risks and to measure and describe them to the fullest extent possible. The specific nature of those activities varies from one risk context to another. Recall that the purpose of risk assessment is to answer the risk manager's science and evidence-based questions. One of the distinguishing characteristics of risk assessment is the fact that it is intentional about describing and addressing the relevant uncertainty encountered in the assessment that could influence the decision or change decision outcomes. There are a few risk assessment principles that we might find rather broad agreement on. These might begin with ensuring that the responsibilities of assessors and managers are separated. Whatever definition or model you use, risk assessment should provide a systematic and structured approach to discerning the truth, and it should be both objective and transparent. When risk assessment is used for anything more than private decision making, it ought to be appropriately documented in a manner that allows for peer review and communication that's suitable for different stakeholders. Ultimately, risk assessment must meet risk managers' information needs for decision making. In considering a definition or model, it's important to recall that risk is not always a monolithic concept. There are many dimensions of risk to consider, including the following: existing risk, new risks, future risk, risk reductions, residual risk, historical risk, geographical risk, temporal risk, transferred risk, and transformed risk. In the United States, risk assessment began to rise to prominence in the 1970s. At the time, there was a great deal of confusion about what this new risk assessment process was. In response to a directive from the Congress of the United States, the Food and Drug Administration contracted with the National Academy of Sciences to conduct a study of the institutional means for risk assessment. The Committee on the Institutional Means for Assessment of Risks to Public Health was formed in the National Research Council's Commission on Life Sciences in October 1981, and it completed its work in January 1983. This work, entitled Risk Assessment in the Federal Government, Managing the Process, is better known as the Red Book, and it provides the first formal definition of the risk assessment process. Its purpose was to determine whether organizational and procedural reforms could improve the performance and use of risk assessment in the federal government. It provided a definition that could be seen time and again in the many risk assessment models in use today. The definitions from that report are worth knowing. Risk was defined quite differently from the definition we use today. It was called a characterization of the potential adverse health effects of human exposures to environmental hazards, and a characterization of the uncertainties inherent in the process of inferring risk. It may be useful to know that the Red Book referred to what was essentially a human health cancer risk assessment technique. Risk assessment was described as a four-step process that included hazard identification, dose-response assessment, exposure assessment, and risk characterization. The steps were defined as follows. Hazard identification determines if exposure to an agent causes an increased incidence of an adverse health effect. Dose-response assessment characterizes the relationship between exposure at different levels or doses and the incidence of the adverse health effect. The exposure assessment measures or estimates the intensity, the frequency, and the duration of actual or hypothetical exposures of humans to the identified agent. The final step in the risk assessment is risk characterization, and this is the step where you pull together all the good science from the three previous steps, and you estimate the probability of a specific harm to an exposed individual or population based on the information obtained from the dose response and exposure assessments. In the next several slides, I'm going to give you some examples of different risk assessment models and ways that people have applied these basic steps. We're going to begin with Codex Alimentarius. That means the Book of Foods, and this is the United Nations organization that is committed to using risk assessment for food safety. They define risk assessment as a scientifically based process consisting of the following steps: hazard identification, hazard characterization, exposure assessment, and risk characterization. What you will see here is virtually identical to the Red Book. The big change is that the second step, dose response, has been broadened and now is considered hazard characterization because there are more ways to characterize hazards than a simple dose-response relationship. These four risk assessment steps are defined in this slide. Hazard identification is the identification of biological, chemical, and physical agents that are capable of causing adverse health effects and which may be present in a particular food or group of foods. Hazard characterization is the qualitative and or quantitative evaluation of the nature of the adverse health effects associated with the biological, chemical, and physical agents which may be present in food. For chemical agents, a dose-response assessment should be performed. For biological or physical agents, a dose-response assessment should be performed if the data are obtainable. Exposure assessment is the qualitative and/or quantitative evaluation of the likely intake of the biological, chemical, and physical agents via food, as well as exposure to other sources, if relevant. Risk characterization is the qualitative and/or quantitative estimation, including attendant uncertainties, of the probability of occurrence and severity of known or potential adverse health effects in a given population based on hazard identification, hazard characterization, and the exposure assessment. Other risk assessment models exist. OIE, the International Animal Health Community, defines risk analysis as shown here. Risk assessment is defined as a 4-step process, but the steps are quite different from the Codex and Red Book models. Note that they include release assessment, exposure assessment, consequence assessment, and risk estimation. Here's a conceptual risk assessment model for a very specific kind of food safety hazard, a food additive. Food additives are chemicals that are intentionally added to foods to improve their flavor, appearance, processing, shelf life, and the like. The process, which is called a safety assessment, begins by estimating an acceptable daily intake. This is an amount of the additive which can be consumed daily for a lifetime without causing any adverse human health effects. It's based on data obtained from toxicological studies, animal studies, and the use of uncertainty factors. Then one calculates the estimated daily intake of the food additive using food consumption surveys and additive concentration data obtained from industry and laboratory analysis. These two values are compared in a simple fraction. An estimated daily intake divided by an acceptable daily intake that is less than 1 is considered safe. Pesticide residue assessment is another chemical risk assessment that's very similar to the food additive safety assessment. The steps include identifying the pesticide residue of interest, undertaking toxicity studies of the substance if they are needed, determining the no observed adverse effect level, selecting a safety factor or uncertainty factor to extrapolate results from animals to humans, then calculate the acceptable daily intake, the ADI. Meanwhile, you would identify a suitable index of residue levels to predict the residue intake on the foods of interest. This is usually the maximum residue limit, or MRL. You would undertake dietary intake of the residue and then compare the exposure to the ADI. When the exposure exceeds the ADI, some sort of risk mitigation is required. Microbial risk assessment has become increasingly important, and it's quite different from chemical risk assessments of the Red Book and food additive safety assessments. For one thing, the hazard is alive in microbiological risk assessment. Microbial risks are usually acute and the result of a single exposure rather than a lifetime exposure, as with chemical risks. There's also complex interaction of pathogen, host, and food. These risk assessments tend to consider a farm-to-fork perspective, and it is always a team sport. No one person can do a microbial risk assessment. There is so much more uncertainty that microbiological risk assessment makes much use of expert opinion. On the right, you see one of the earlier microbiological risk assessment models. The steps are identified as problem formulation, analysis, and risk characterization. But a careful consideration reveals that the analysis exists of an exposure assessment and a hazard characterization, along with a risk characterization. So this first and early microbiological risk assessment model is not too much different from the Codex model we looked at a few slides back. Antimicrobial resistant risk assessment tends to be qualitative in nature. Notice that it follows the animal health risk assessment model. We see hazard characterization, but the actual qualitative risk assessment comprises the steps that you see there on the left: release assessment, exposure assessment, consequence assessment, and then jumping to the right, risk estimation. Pest risk assessment decomposes the basic risk equation. Perhaps you'll notice the similarity to the glimmerous risk assessment, which was actually an adaptation of the model that you're looking at here. Biotechnology risk assessment relies on safety assessment that is built on a comparison of the genetically modified food with the traditional food that has a history of safe use. Unexpected differences between the two foods define the need and extent of further safety assessment. This comparison tries to establish a substantial equivalence between the two foods. Notice how this nutrition risk assessment model echoes the Red Book. The 4 steps are very similar and are modified to meet the needs of the nutrition community. You see hazard identification and hazard characterization. In this instance, exposure assessment has been modified to be a dietary intake assessment. The familiar risk characterization step is seen here as well. This Nano risk assessment model resulted from an unusual collaboration between DuPont and the Environmental Defense Fund. The upshot of all this is that there is no one best way to do or to define risk assessment. Different communities of practice would have different risk assessment models, much as the food safety community has. Consequently, I like this model. It serves as a generic risk assessment model that can be used until your community of practice develops a model more to its liking. The 4 steps are: look for the hazard or opportunity. Here you would identify the hazards that can cause harm, or you identify the opportunities for gain that are uncertain. This is followed by a consequence assessment. Here you decide who or what may be harmed or benefited, and in what ways. You gather and analyze the relevant data, and then characterize the consequences and their uncertainty, doing this either qualitatively or quantitatively. There is also a likelihood assessment. Here you assess the likelihood of the various adverse and beneficial consequences. You would characterize these likelihoods and their uncertainty qualitatively or quantitatively. The last step in this generic model is risk characterization. Here you estimate the probability of occurrence, the severity of adverse consequences, and the magnitude of potential gains, including the attendant uncertainties, and you do this for the hazards and the opportunities identified based on the evidence in the preceding steps. You characterize the risk qualitatively or quantitatively with appropriate attention to baseline and residual risks, risk reductions, transformations, and transfers. Questions are welcome. I will see you back in the class.